Today's goal is to determine two-sided limits using a graph or a substitution. So we already know how to evaluate one-sided limits. For example, we know that the limit of the function as x approaches a from the left means we're tracing along a function to see, let's for example say we're approaching the x value 2 from the left, so we're tracing, excuse me, to the left of the x value 2, and we get really close to the y value 1. And we know that the limit of f of x as x approaches 2 from the right means that this time we're going to trace to the right of 2 and get closer and closer to the y value, which gets close to the y value negative 1. So the two-sided limit would be asking what is just the limit of the function as x approaches 2, meaning both from the left and from the right. Well, in order for a two-sided limit to exist, the one-sided limits, the limit approaching from the left and from the right of a function, they must both exist, and the one-sided limits must both be equal. So there is the limit of the function as you approach 2 from the left and 2 from the right, but these two limits aren't the same. So we would say that the limit of the function as x approaches 2 does not exist. Let's take a look at a couple other examples from this graph. What if we were trying to find the limit of the function as x approaches negative 2? Again, it's not just from the left, it's not just from the right, so this is a two-sided limit, which is asking us, well, what's happening with the function as you get close to the x value negative 2? Well, if you approach from the right, we are approaching the y value 1. But from the left, there isn't anything, right? This is all just blank space. The function doesn't exist to the left. So we would say the left-handed limit at negative 2 doesn't exist. Therefore, the two-sided limit at negative 2 also does not exist. Let's take a look at one more example from this graph. Maybe two examples. Let's take a look at the limit of the function as x approaches 1. Well, from the left of 1, we're getting close to the y value 2. From the right of 1, we're getting close to the y value 2. The left and the right-handed limits both exist, and they're both the same. So the two-sided limit, is 2. Let's take a look at one more example. What about the limit of the function as x approaches 0? Well, if you're getting close to 0, whether you're approaching from the left or the right, we're approaching the y value 1. It totally doesn't matter that the fact that f of 0 is 0, right? The y value at the x value 0 is actually 0. That doesn't matter. The limit is simply asking if you get really close from the left or the right, what's the y value that you're getting close to? Okay, let's take a look at another example. Here's another graph. For which values a on the function below do we conclude that the two-sided limit, so the limit of f of x as x approaches a, does not exist? Justify each choice. Well, let's actually just trace from left to right and see sort of what's going on here. So the function appears to go forever in this direction. Maybe it hits an asymptote, meaning by hits I mean gets close to. And then we notice that there's a vertical asymptote at negative 2. And there's some scholarly debate here as to what to say about whether or not the limit of the function as x approaches negative 2 exists or doesn't. So you could either say that the limit of the function as x approaches negative 2 does not exist, or you could actually say that this limit is equal to negative infinity, because on both sides, whether you're approaching the x value negative 2 from the left or from the right, on both sides you're going down sort of infinitely. So either one of these have been acceptable in different textbooks. Let's take a look at negative 1 though. As you approach negative 1 from the left, you're approaching the y value 3, but the right-handed limit would be negative 1, and so the limit of the function as x approaches negative 1 also doesn't exist, since the left-handed limit and the right-handed limit are different. They're not equal. Okay, everything else looks pretty normal until we get to the x value 1. And we notice the left-handed limit is positive infinity, and the right-handed limit is 1. So the limit of the function as x approaches 1 does not exist, since the left-handed limit and the right-handed limit are not the same. And then finally, the limit of the function as x approaches 3 does not exist, since the function doesn't exist to the right of 3. So the right-handed limit doesn't exist. Okay, let's take a look at the same graph and ask ourselves, for which x values, we're calling them c, is the y value different from the limit? That's like saying, when is perception and reality different? When are you approaching something different than you would actually be equal to? So these c values, well, certainly -2, because the limit is -infinity, but f of -2 is 3. Also -1, since the limit does not exist, but f of -1 is just 2. Also 1, since the limit of the function as x approaches 1 doesn't exist, but we know that f of 1 is just 2. That y value is defined right here. We would also say this is true at x equals 2, because the limit of the function as x approaches 2, well, the limit's right there. You're approaching the y value 2, but f of 2 is undefined. We don't have a definition for it because there is no closed circle anywhere where the x value is 2. And then finally, as discussed, the limit is different from the y value at 3 because f of 3 is defined. F of 3 is just 3, but the limit of the function as x approaches 3 does not exist. Let's take a look at some piecewise examples. We're going to try to find a couple of different limits. Now, when I think about this piecewise function, sometimes it helps me to just get a sense of what's going on here in terms of the x values. So this first function, we can think of it as the quadratic piece, is happening where x is less than -5. So I'm just going to sort of label that. And then this next piece, the exponential piece, 2 to the power x, which we all know is the same thing as 1 times 2 to the power x, that's happening from the x value 5 up to the x value 8. And then we've got a gap here, and from 10, but not including, 10 to 12, that's where we have this radical piece of the function. And then finally we have a linear portion, where x is greater than 12. And so sometimes that just helps me sort of catch a sense of what's happening at these different x values. So I can see if I'm trying to find the limit, the two-sided limit as x approaches -5, well, when I approach -5 from the left, I'm approaching on the quadratic piece of the function. And when I'm approaching from the right, I'm approaching from the exponential piece of the function. So this two-sided limit will only exist if the two one-sided limits both exist and are the same. So we actually have to test each of those. So we have the limit of g of x as x approaches -5 to the left. Well, let's take a look at this quadratic piece. We'd have -5 plus 7 squared minus 3. So we'd have 2 squared is 4 minus 3 is 1. And on the right-hand side, the limit of the function as x approaches -5 from the right. Now I need to see what's happening on the exponential piece. So I have 2 to the power -5, which is 1 over 2 to the 5th, which is 1 over 32. And I can see that the left-handed limit and the right-handed limit are not the same. And so the two-sided limit does not exist. But g of -5, well, I can see that the closed circle is on the exponential piece. So g of -5, I've actually already done the substitution and already done the simplifying. G of -5 is 1 over 32. Let's take a look at a few more. What about at 8? Well, at 8, we know that the function isn't defined between 8 and 10. So the right-handed limit simply does not exist. So the two-sided limit also will not exist. But g of 8 is defined because there's a closed circle here. So to find g of 8, we're going to substitute 8 into the exponential piece. So g of 8 is 2 to the power 8, some giant number that we don't really have to evaluate. What about the two-sided limit where x approaches 12? Well, at 12, we're going to have to check again the left-handed limit by looking at this radical piece. So I've got root 12 plus 4 plus 7, which is the square root of 16 plus 7, which is 11. And now let's check on this linear piece to find the right-handed limit, which will give us 12 minus 1, which is also 11. So since the left-handed limit and the right-handed limit exist, and since they're the same, we conclude the two-sided limit is 11. And g of 12 is undefined. There is no closed circle. There isn't an x value 12 in this function. And then finally at 13, 13 is right smack in the middle of this linear piece. And so we can simply substitute into the linear piece, and we know that the limit of the function as x approaches 13 is just 12. And also g of 13 is also just 12. Because we'd be approaching from both sides on the same function. We know that linear functions x minus 1 is going to look like this. It doesn't have any like gaps, any asymptotes, or any jumps like we see here. It doesn't have any gaps or holes or missing pieces. Linear functions just look like this. There's nothing weird that we need to look out for in terms of the limit. Let's take a look at one more example, and these examples are just to remind you that when you're trying to find the limit, your first and foremost tool is always just substitution. We know that this is a rational function. Maybe we're remembering it's a rational function that'll have a vertical asymptote at 4. So it'll look, I don't know, something like this, roughly. But as x approaches 9, nothing weird is happening. So we can just substitute most of the time to find limits. And likewise, when we're looking at 2 times 3 to the x, well, we know that's just an it's just an exponential function. There aren't any weird gaps or holes or breaks in the graph, so to find the limit, we're just going to substitute. And anything to the 0 power is 1, so the limit is simply 2.